Good morning, everybody. Now the geological setting session opens with 4 very interesting contributions on the topic of the session. We will start with the first contribution by the title, The Fleche Rosso Formation, Southern Apennines, Lithological and Structural Features and the Challenges, and the Geotechnical Modeling and Characterization, will be presented by Professor Gianfranco Urcioni. Please, Professor.
Thank you, Mr. Chairman. Okay, I hope that you can see my presentation. The title of my presentation is The Fleche Rosso Formation, Southern Apennines, Lithological and Structural Future and Challenges in the Geotechnical Modeling and Characterization. The Fleche deposits consist of alternating and highly deformed or completely disarranged rock and marly or clay shell layers, which are often involved in slope movements. Their intrinsic lithological heterogeneity and complex fabric, along with the high perishability of the fine structure component, make extremely difficult any mechanical soil characterization for engineering purposes. In order to address the problem, in the 70s and the 80s of the last century, some important research projects were funded by national agency and national scientific community, which allowed to gain some knowledge about the general feature of this formation and the hydraulic and mechanical behavior over the fine-grained component. The Apennine chain is a neogenic chain formed by the overlapping of several Mesozoic tectonic units, mainly made up of carbonate basin and interreginous succession. The basin and interreginous succession, the Fleche formation, which are the focus of my presentation, are both characterized by the interlying of sedimentary rocks, sandstone, limestone, conglomerates, marls, and clay deposited in different environments. During the late Miocene and Pliocene, the compressive tectonic regime strongly deformed this sedimentary succession, leading to formation of faults and of faults. The fine-grained soil experienced also some metamorphism and mineralogical modifications. The well-known red fleche, which is described in this presentation, represents the best example of the effects of tectonism on fine-grained materials. In fact, the soil appears as heterogeneous masses with strong vertical and horizontal lithological variation. A schematic synthesis of the geological history of this tectonized formation, including the effect of weathering and softening phenomena, is shown in this figure. Fleche deposit has the red fleche, are typical example of the so-called structurally complex formation. As you can see in the classification by ESO, like to call a wide spectrum of materials. The basic feature of the structurally complex formation are a small porosity and weak bonding materials which affect the soil macrostructure, and the meso and macro fabric characterized by an intrinsic lithological inhomogeneity and by widespread smaller persistent discontinuity has fissure, cracks, joint, shear surface, which play a major role on the hydraulic and mechanical soil response. The classification of structurally complex formation is just based on lithological feature and meso-macrofabric of the material. It identified 3 distinct classes of soil, schematically represented in the figure, where a metric scale is also reported to help the reader to get a clear idea about material appearance. The second class, type B, includes flysch, alternating layers of rock and of hard, often fissile-structured fine-grained soils on Mars. This class is further subdivided into 3 subgroups, the difference depending again on material microfabric, which may be quite regular or highly deformed by tectonic stress. A fragmented mesofabric is a typical feature of the fine-grained component of a class B. In B1 formation, it generally consists of millimetric to centimetric hard platy fragments, bounded by polished fissure parallel to the layer. This is the typical macrofabric of fissile material, which have been subject to high compressive stress, leading to some orientation of clay particles. Stress release favors the formation of parallel fissures. The macrofabric of B2 and B3 deposits more clearly reveals the effect of tectonism. In this case, the material consists of small millimetric to centimetric fragments or scales, bounded by polished and often slack-sided surface. An example mesofabric of a clay interbedded between calcareous layers is reported in this figure, which saw 3 specimens subject in the laboratory to direct shear test parallel to bedding. The studies by Riedel and more recently by Skempton and by Morgenstern Chalenko could help in the interpretation of the mechanical process leading formation for the shear lenses. As shown by Riedel, through sort of simple shear test in which the mechanism of soil failure is imposed by the boundary condition, soil failure in fine-grained soils is preceded by formation of short shear surface called minor shears, known also as Riedel and thrust shears, inclined to the direction of shears. The angle of inclination is a function of the local direction of the principal stress. The rupture process is then accomplished by formation of a major and persistent shear surface, the principal shear, in the imposed direction. In this final stage, the shear zone is a thin band where short inclined fissure and the principal shear coexist. Chalenko remarks that the same fissure may be found in the field at very different scales. As remarked by Piccarelli et al., it appeared that quite obvious the shear zone can be generated by different phenomena such as folding, faulting, ice thrusting, valley erosion, and consequent lateral spreading, and so on. In particular, the slip surface of landslides should coincide with the principal shears that develops in the latest stage of the failure process. An example of shear zone at the base of a slide in a highly overconsolidated clays was reported by Skempton and Petley. The principal stresses can rotate, plastic adaptation, leading to formation of further less inclined shear anti-soil failure, which take place when plastic shear strain can eventually develop a line compatible with large displacement. The red flysch is a typical structurally complex flysch formation, class B, which in the 18th of the last century had been the object of studies aimed at the study of some order flows in an area close to the town of Potenza. Presently, an in-depth campaign of investigation has been carried out in some kilometer section in the Campania region. The red flysch, which largely crops out in the southern Apennine, belong to the Lago Negro Molisano Basin Paleogeographic Unit. In the investigated area, the Grottaminarda Melito section have been carried out 110 boreholes reaching depths comprised between 30 and 100 meters, 4 cross-hole and 1 downhole test, 10 shallow geographical tests covering a total length of 5 kilometers. As already mentioned, the formation presents both lapidus and fine-grained components. Regarding the pelitic components, different types have been recognized. In particular, the study has been focused on the valley-colored scaly clay shales, that is the type 1. Here, the scaly gray marly clays, type 2, are shown. These one are the oldest one from tertiary age, which underwent high tectonic stress during the compressive Pliocenic phases that lead to formation of the Apennines change. Both types, which have been subject to laboratory investigation, display evident polished shear surface. In addition to types 1 and 2, further pelitic components, such as red clays and marls, have been recognized. This is the group number 3. Analyzing grain size and plasticity, the mean value determined are very similar to each other, or the dispersion of data is so high that the comparison of average value does not allow to appreciate any difference. The geological survey and many boreholes carried out in the study allowed to identify the stratigraphic subsection of the red fleece formation, which is generally treated as a homogeneous formation in the practice, being in contrast an extremely complex succession of materials. 7 phases have been recognized, all of them characterized by the presence of clay. The figures show the stratigraphic sequence. The deepest members include the calcareous deposit having a thickness of 10-15 meters with metric intercalation of marl and varicolored clay shales. In this slide, B1 phases are shown. The subclass by B1 consists of regular succession. The sand-shale ratio is highly variable from case to case. The rock layer presents closely spaced vertical joints, and the clay shale interbeds are highly fissured, with fissure usually parallel or normal to the layers. The subclass B2 consists of highly deformed and disarranged materials. In fact, the lapidus component has lost its original spatial arrangement, forming folded and discontinuous layers with joints filled with clay. The class B3 consists of completely disarranged materials. In fact, the lapidus component is reduced in the form of isolated rock blocks scattered into a highly fragmented fine-grained matrix. The rock component varies from 20 to about 70%. This means that the mechanical behavior of the formation can vary from that of the clay matrix, completely indifferent to the presence of rock elements, to that of a rocky medium weakened by the presence of clay layers. In these two sections, covering a distance of about 5 kilometers, you can see how the phases alternate and the lithology is variable even at a distance of a few hundred meters. In conclusion, we can conclude that comparatively significant lithological and structural difference that exist between the phases and that will be described later, that it is described, the difference attributable to the different nature of the pelitic component don't seem to be determining. Much more significant is the volumetric ratio of the clay and rock components to the total volume, the continuity and the orientation of the rock components. Thank you for your attention.
Thank you, Professor Urcioli. Your presentation is very interesting. The next contribution by the title, Role of Flysch in Large-Scale Rock Avalanches Formation in Eastern Sector of the Alpine Mediterranean Belt, will be presented by Professor Alexander Strom, my great friend.
Thank you. Colleagues, do you hear me? Hello? Do you hear me?
Yes, yes, we can hear you, Professor, yes.
Okay, just a moment. You see, I don't know why, but camera don't want to show my face. I will present. Do you see my screen, colleagues?
Yes.
Yes, yes.
I will start, thank you.
Yes.
So this presentation was prepared together with Professor Oleg Zerkal from Moscow State University. Generally, the stratigraphic successions of relatively soft terrigenous flysch overlined by carbonate or volcanic clastic formations are quite widespread in the eastern sector of the Alpine Mediterranean belt. And such relationships form very good prerequisites of the formation of long run-out rock avalanches, most of which in the study area had occurred in the middle or late Neopleistocene. And I will present several examples of such phenomena from the Crimean Mountains and from the Greater Caucasus. And I will also discuss the possible mechanism of their formation. Generally, flysch that is quite typical of this area, the terrigenous flysch, can be divided into several, let's say, several types. In the Crimean Mountains, the Triassic and lower Jurassic flysch, the so-called Tauric series, is the classic type of the turbidite flysch formation. It is composed of the clay stone mainly, you can see on the image, and the subordinate sand or siltstone layers. Generally, it reached the argillite stage of the catagenesis so that the clay stone is not soaked and is weathered up to fine rubble only. More or less similar properties has the Jurassic flysch in northern Ossetia that underlies the 1 kilometer high cliff of the Caucasian rocky range. In contrast, the Jurassic flysch at the southern side of the Greater Caucasus in the Sochi-Mazinto region is composed of cyclic units, predominantly argillaceous too. But here, unlike the Crimea and northern Ossetia, clay stone is swelling, thus it did not reach the same stage of the catagenesis as in Crimea. Here we can see the central part of the southern coast of the Crimean Peninsula with 6 very large rock avalanches, largest of which exceeds 1 cubic kilometer in volume. The upper plateau-like area is composed of harder rock, of limestone and sometimes of conglomerates, while the lower part of the slope is composed of flysch. And here we can see some examples. It is the Sotera rock avalanche, and you can see completely crushed and pulverized flysch at its distal part above and at the basal faces below. And another case study, the Kanaka rock avalanche, brecciated flysch of its central part. And if we compare it with the bedrock flysch, we can see the extent of deformations of this material. Now let's go to Sochi region. There are frontier rock avalanche in the Mazinto River Valley, It had originated from the upper part of the Aibga range, composed of flysch, overlain by porphyry series of Jurassic age. Here you can see the digital elevation model visualized by some software and made by laser scanning. And we can see the headscarp of this rock avalanche, its body, and the total runout was about up to 5 kilometers. And deposits rest on the second terrace of late Pleistocene age. The total volume of the displaced material here was estimated as 150 million cubic meters in volume, quite large feature. And again, now we can see the material. It is the carapace facies composed of large angular blocks of volcanic rocks here and here. And here we can see the intensively fragmented body facies with very rare angular boulders. A large part of this material was composed of flysch involved in this rock avalanche. The third example is from Northern Ossetia. It is on the northern side of Greater Caucasus in its central part. Here you can see the cross section of this so-called rocky range, and we can see the location of these rock avalanche deposits at the southern feet of this rocky range. Here is the distribution of rock avalanches in the Ardonne River Valley. It is the Ardonne River. Here we have at least 1, 2, 3 very large rock avalanches, and most interesting in the content of our presentation is not this gigantic one, the Karif Hoch, about 2 cubic kilometers in volumes, but these two, Upper Missour and Sularta. What is interesting here? Rock avalanche deposits rest in the old valleys of the Ardonne River tributaries that and fill them almost completely. Here we can see the carapace facies of these deposits, and here we see the body facies of the that can be found in some erosional gullies where material was crushed at a very large extent, sometimes up to powder. What is interesting here, that in front of these bodies composed of fragmented limestone, on the gully walls, we can see remnants of flysch material completely pulverized, sometimes with boulders of flysch in flysch matrix that were bulldozed by the main body of rock avalanche and now remains at the gully slopes closer to Ardonne River Valley, which is here. The bedrock here is also flysch, but its other part, lower part, which has much larger content of sandstone and siltstone, while this material is composed mainly of argillites or clay stone. And here is the cartoon illustrating formation of rock avalanches at the southern cliff of Rocky Range. And generally, we assume that some similar mechanism can take place in all cases described above. At some stage, we had this Ardonne River, this high cliff of Rocky Range composed of limestone, and then tributaries of Ardonne cut through here, and finally they undercut the base of this high cliff, and slope failures occurred only at those sections of this rocky range where its foot was undercut by this backward erosion. We anticipate that due to enormous weight of this rock massive, the weak flesh could not sustain and was somehow deformed and pressed out here, something producing something. It is not clear classic buckling, but some pressing out. And finally, it resulted in failure of this rocky slope composed of hard rock and in formation of rock avalanches that rushed ahead, pushing this flesh material in front of it. And now we will come to conclusions, so that conclusions are that presence of the relatively weak flesh at the base of high slopes, which upper parts are composed of hard rocks, such as limestone in Crimea and northern Ossetia, or volcanic rock, as in Mazinto River Valley. It forms the prerequisites for formation of large-scale rock slope failures that often convert into extremely hazardous rock avalanches. Slopes with such combination of lithological units should be considered as potentially hazardous and rock avalanche prone. And high risks here are predetermined by the extreme mobility of large-scale rock avalanches that can affect areas located not only just at the feet of such slopes, but kilometers far from them. The question still remains why we have so many such rock avalanches in the past and why we do not have them at present. We do not have a real answer for this question, but we can assume that it could be somehow associated with different climatic conditions that had existed at the time when these rock avalanches had been formed. Thank you for your attention.
Thank you, Alexander. Your presentation is very interesting.
Thank you.
Now, the next contribution have the title Landslide Characterization in the Polong region, Macedonia, by Innovative and Conventional Methods. Will be presented by Professor Igor Peshevsky. Please, Professor.
Thank you, Matt. Thank you very much, Professor. Can you hear me?
Okay.
Okay. So the paper was prepared by a team from University of St. Cyril and Methodius in Macedonia, and from Italy were included the University of IREA Institute. And as said in the title, we tried to characterize landslides, in particular region in Macedonia, by innovative, for us it is innovative, and some conventional methods. The outline of the presentation, we're going to give a small introduction of the problem, the case study area, what is the geological context and the landslide connected to it, and we will present the landslide characterization. After that follows the conclusions and discussions. Below you can see several pictures of landslides from the region, which we will see now. Macedonia is severely and frequently hit by landslides, and the Polog region, we will see on the next slide where it is situated, is the most prone to landsliding due to the complex geological, morphological, and tectonic settings. As a result of this, there is a necessity for appropriate risk management for this part of the region, and the country and let's say other financiers are trying to do something in this direction. Inventory is a prerequisite for preparation of good susceptibility and hazard models. So the first step is to make a landslide inventory, which will be reliable and upon which we can and calibrate all future models. So this, in a way, will enable systematic approach in the management of landslide hazard in general terms. The main three, let's say, facts for this study are that we used conventional methods. We analyzed geological and geomorphological maps for, let's say, for detection of landslides, and we also have some scope of field work. After that was satellite remote sensing by DINSAR technique, which is applied actually for the first time in Macedonia for these purposes. And after that, we did some simplified numerical analysis related to generation of susceptibility maps, which were done on the regional scale. So this is the location in Europe of Macedonia, and this part, the Polog region, is on the most northwestern part of the country. You can see the various geological rock masses or lithological types which are present in the region. It's a very complex, as I said before. We also have a tectonic uplift of this part here. This is Sharamau area of the Polog region. Just in order to see how it is standing in relation to landslide susceptibility in relation to Europe, I have put this map of the ELSUS project, the newest version, and this is the polygon that we're looking at. So we can see that is in a very high susceptibility zones, according also to this, let's say, continental susceptibility map. The slope maps and the rainfall maps of the region, we can see that the slopes in some places go over 55%, and there are many other places, let's say from 25 to 45. So it is characterized by very pronounced morphology. And this is the rainfall map, unfortunately generated with very small amount of data, but we can see there is differences in the rainfall distributions. And also this part is over 900 millimeters per year. Actually, in some places we have even over 1,200 millimeters per year. This is some previous work which we have. So it's a, let's say, heuristic approach to prepare a susceptibility map. This is presented elsewhere, and these dots that you see, these are maps which were invented at that time by using only satellite imagery from Google Earth and some other sources, but let's say it is more basic with not so much verification of the landslides as we will see in our paper now. These are some of the most recent events, pictures from the most recent events. This is from 2015. We have several types of landslide occurrences in one case of extreme rainfall, which occurred on 3rd of August in 2015. So we have, as you can see, debris types of, let's say, landslides in most of the cases. And this is actually something we were not able to see in the older landslides. They were all treated like rotational, translational, you will see later on, but only one is actually classified like a debris event. So this is one issue which requires a little bit more study into the future. This is the results from the, let's say, prepared inventory in the frame of the project. As you can see, for the landslide trigger, for example, we have 85 landslides, which we don't have any information how did they initiate it. The database is actually 136 landslides, so this means that for more of 2/3 of the landslides, we don't know the exact trigger. After that, the landslide classifications, as you can see, only translational landsliding, we have 40, let's say, confirmed mechanisms, and for the half of the landslides we don't know the mechanism, so we only have outline of the landslide. In relation to the state of the activity, at the moment we have around 37 active landslides and 80 landslides which are unknown if they are moving. And in relation to the depth of the sliding surface, let's say on 2-meter depth is the border, we have 39 deep landslides, 29 shallow ones, and for 68 we don't know the exact depth. So from the analysis of all landslides in the inventory, we came up with this, let's say, facts that the most important parameter is the lithological composition. We are talking about presence of tectonically affected Precambrian metamorphic complexes of bedrock, and which is overlain by thick, let's say, layers of the most landslide develop along this contact between the debris and the schist bedrock. And from, let's say, more from experience, we know that the main triggering factors are the intensive rainfalls. So this is the, let's say, this distribution of the landslides in the region. And these are some, let's say, cuts to see, let's say, position in order to, you see here some village we have. Here also we have, this is on somewhere here, A3. So we have, for many landslides, we have very strong interaction with the built-up environment. So with villages, let's say some structures for production of hydroelectric power, etc. The next step was to apply some, let's say, innovative technique, and here by this we mean the application of DINSAR technique. So in first stage was prepared a priori visibility map, which showed that the coverage, let's say, from the Sentinel is not so good for this region. However, everything which was possible to interpret in some way was taken in consideration. Here we can see some of the results. So there, this is the map actually here of the Persient scatterers that were defined into the region, period of 2015 to 2019. And these are some of the landslides, the outlines of the landslides from the database, and how the permanent scatterers are placed into their surface, let's say. These are some of the results of permanent scatter number and what are the distances recorded by the DINSAR analysis. This was for the, let's say, one stage of the DINSAR technique application, and the other one was to detect hotspots which were not identified as landslides in the current inventory. So these are actually indications that DINSAR gives that there is some type of movement. So these are a subject of further investigation in future stages. We have somewhere around 40 of this type of locations which need further studying. As a final stage was preparation of susceptibility map based on the, let's say, available data in the inventory, which is not very, let's say, rich. And because of that, there was no, let's say, rational basis to continue with preparation of hazard maps. So that's why were prepared only landslide susceptibility maps. Two basic models were prepared. One is related to the debris flow modeling, and the other one is for shallow landslides. And this is some of the input data that we have used. It is interesting to see that now we have a LiDAR survey of the study, which came a little bit later into the, let's say, into our project. And because of that, here I believe, or the team believes, that we have a lot more to do with the LiDAR now. So this is some future stage of investigation. The debris flow modeling was based on the FLOAR software, which is a, we all know, regional model. Here are some of the input parameters into the analysis. And it is worth mentioning that we have prepared like filter maps, let's say, for in relation to the geology. So we delimited zones which are not so favorable to develop a landslide. And we did the same for the Curine land cover, like a layer. And we cut out some zones which we believe are not possible initiation zones. We have analyzed the possible data on the rainfalls in relation to intensity duration correlation. And unfortunately, there are only 2 measuring stations of the rainfalls with very, let's say, reliable data. And it came out that when we compare with other studies in similar geomorphological conditions, we see that all the combinations are possible for intensity and duration to develop a debris flow. So the rainfalls were actually after that excluded from further analysis. And this is the final map for debris flow modeling that we have obtained. This is one polygon, which here you can see in a little bit larger scale. So we can see that the blacks are the possible debris paths, and the blue are the infrastructure and the built-up area. And we can see that we have very strong interaction in some places. So the hazard is present here. The next model was the shallow landslide susceptibility assessment. The Skempton and Delori equation was applied, or the infinite slope method. We know that there exist a lot of variants of this infinite slope method, and this is the equation that we actually have used. So we have taken also into consideration the cohesion of the soil, but also from the root cohesion. It is, let's say, with very small amounts, with very low values, but anyhow, we wanted to include it into the model just to be as more precise. So these are some of the, let's say, input parameters for the unit weight of the dry soil, of the saturated soil cohesion, and internal friction angle for different, let's say, sediment which are present into the study area. And some of these were taken from engineering geological map of the country, and some of them were assessed, let's say, by experience. And we have prepared several models of the shallow landslide susceptibility assessment. These are here the cohesion from the roots of the vegetation. This is some of the results. So here we have shallow landslide model with minimum values of the geotechnical parameters. So this is the worst case scenario. And we have taken into consideration 35 saturation of the soil and 70%. So these are the 2 maps which we obtained, and these are the classes of the stability of the terrain. So we see that we have a lot of red on the map in the case of, especially in the case of 70% soil saturation. And we can see that we have generally a good, let's say, correlation with the locations of the known landslides with the, let's say, unstable and quasi-stable zones as we have defined them into our model. So in relation to the safety factor. The following 2 pictures are for the average values of the geotechnical parameters. So we can see that we have now reduced zones of the high classes of landslide susceptibility. Anyhow, they remain into the same context or the location of the landslides generally very well. It is corresponding to these zones. As a discussion and conclusion, we can say that the preliminary landslide inventory and susceptibility maps, along with the DINSAR data interpretation, are considered satisfactory for the regional scale study. The obtained results helped us to delimit watersheds in the region, which required more advanced study. And we have the chance now to prioritize landslide requiring detailed investigations and define which landslide need monitoring. This part, the INSAR was very, let's say, helpful. After that, depending on the landslide typology, it can be seen that the delimited zones with high susceptibility to shallow landsliding match with the most landslides from the inventory. We saw that on the previous two pictures. In relation to flow-like events, it is seen that the adopted model is governed by the morphology of the terrain, while the verification is not possible at the moment because we don't have landslides in the database, which is debris flows. And another limitation of the debris flow is that the rainfall data is very limited. And the field surveys show that the applied spreading algorithms give higher values of the susceptibility for the higher elevations. So we have a lot of, let's say, deeply fractured rocks here, but in reality, they should not develop into debris flows, having in mind the rock blocks. After that, the shallow landslide model is also limited. We don't have detailed data on the soil thickness, and we have relatively low number of data of the geotechnical parameters, also on the groundwater. So many of this data is taken from older maps. For the size of the region, we now believe that the next step is to continue with the watershed analysis. And also, as I said, we have the LiDAR data now available. So it means that a lot of work is still before us. Okay, this is something for the future studies. I already said this. And at the end is the final, let's say, map, combined map of all the hazards. So of the shallow landslide model and the debris flow model, along with the denser, let's say, indications. We have some very good, let's say, correlation among all of the analyzed models. So this gives us, let's say, a good motivation to continue on with the analysis. At the end, I would mention that the present work was carried out in cooperation between the Salerno University and University St. Cyril and Methodius in Skopje, and the founding was done by the Swiss Agency for and Cooperation and UNDP. So that's it, and thank you for your attention.
Thank you, Professor Pesceski, for your interesting contribution. And now the last contribution by the title, Landslide Susceptibility Assessment in the Southern Sector of the Tamarro River Basin, Italy, will be presented by Professor Ranaldo. Please, Professor Ranaldo.
Thank you. And, can you see the presentation?
Yes,
Can you
yes.
see the presentation?
Yes, Mirko.
Yes.
Thank you. Hi, everybody. This is Mirko Ranaldo from Napoli Federico II University. Today, I'm going to present our work, which is related to the landslide susceptibility assessment in the southern sector of the Tamarro River Basin. Structurally complex formations are widespread throughout all the regions of southern Italy, where they represent a major concern, especially as regards the safety of urban areas and infrastructures. Therefore, in such regions, slow-moving, intermittent landslides are a recurring phenomena which still deserve the highest attention in terms of their predictability. Here you can see the outline of my presentation, which aims to assess the landslide susceptibility of 73 square kilometers of hilly territory affected by a variety of landslide types. The southern sector of the Tamarro River Basin, which correspond to the municipalities of Paduli and Pietrelcina, is located in the southern part of the Apennines Fault and Thrust Belt. The geological bedrock is characterized by the tectonic superposition of Meso-Cenozoic pre-orogenic sedimentary succession, unconformably covered by Miocene-Pliocene wedge-top basin deposits and quaternary post-orogenic sediments. In particular, the pre-orogenic sedimentary succession outcropping in the study area are known in literature as varicolored clays, a structurally complex formation well known for its susceptibility to landsliding. In the photos are shown some outcrops of the varicolored clays, which correspond to B1 and B2 classes of the ESO classification. In the last 15 years, 3 different landslide inventories in the Benevento province have been carried out by researchers by the Southern Apennines hydrographic districts and finally within IFI project. The number of landslides varies between 100 and 300. Furthermore, as it can be seen in all of them, the most common type is earth flow. Numerous methods have been proposed in literature for the landslide susceptibility assessment in structurally complex formation. For example, heuristic, deterministic, and statistical methods. Among the statistical methods, quite diffused are those based upon the so-called slope units, which try to statistically correlate landslides with geological and geomorphological settings. In our work, we adopted a procedure based upon the homogeneous territorial unit method, schematically shown in the flowchart. Which has been already successfully tested in other districts of southern Italy. It starts from 3 basic maps: geology, geomorphology, and landslide inventory. By grouping geological formation and geomorphological elements, a quite small number of geolithological and geomorphological districts have been defined. Combining both groups of districts led to the homogeneous territorial unit map. Then, the application of a statistical method led to the homogeneous territorial unit susceptibility. More in detail, homogeneous territorial unit susceptibility is evaluated by a landslide index and an activity class, which correspond to the percentage of a homogeneous territorial unit area affected by any type and activity of landslide deposit. To this aim, a statistical analysis using the standardized distribution is carried out as follows. The natural logarithm is calculated for each landslide index. A mean and standard deviation of the values obtained are calculated. Then each landslide index is standardized, and finally the standardized values are classified in 4 classes. Instead, landslide scenarios map was produced from the landslide inventory map, taking into account the state of activity and the intensity in terms of maximum expected velocity of landslides, where low intensity are landslides characterized by low expected velocity. Medium intensity are landslides characterized by average expected velocity, and high intensity are landslides characterized by high expected velocity. The geolithological map derives from a reinterpretation of previous knowledge, integrated with further data carried out during in situ geological surveys. Hence, 13 geolithological complexes were identified for the study area. For example, as you can be seen from the photos, some of those geolithological complexes are clay marly calcareous, calcareous marly, argillitic marly calcareous, and sandy complexes. The geomorphological map was built by means of field survey and aerial photo interpretation, paying particular attention to those geomorphological elements notoriously influential on landslide processes. Thus, 19 geomorphological elements were identified for the study area. In the following photos are reported some of those geomorphological elements. For example, Kalanki badlands, regular sloping ridge and slope sector with few gullies, active detrital alluvial fan, and fault facet. In the landslide inventory map, 303 landslides have been identified over about 73 square kilometers of hilly territory. Also, in this case, through field work and aerial photo interpretation. Particular attention has been given in mapping the largest landslides and in deciding whether they represent an individual slope failure or the result of 2 or more coalescent landslides. On this basis, the landslides were classified in 127 earth flows, 87 rotational transitional slides, and 89 complex phenomena. For example, earth slide, earth flows. Some of those landslides show their susceptibility as potential landslide dams, as reported in Corniello et al. 1980 for Serra delle Forti landslide, shown on the top right photo. So, the inventoried landslide were classified in terms of their intensity, as expressed by the maximum expected velocity. For the study area, only average intensity landslides have been identified, and using the matrix reported in the table, it was possible to draw landslide scenarios map. Accordingly, only the intermediate landslide scenario class LS2 has been identified for the study area. To evaluate the landslide susceptibility, the geolithological map and the geomorphological map were overlapped in GIS software. By using the statistical method and applying the matrix here shown, it was possible to attribute a distinctive level of susceptibility to the different homogeneous territorial units. In addition, a new class of susceptibility called HTU S5 was introduced. This class identifies all the areas where the susceptibility level should be defined after a detailed geological technical study. Finally, the results consist in the overlapping of the landslide scenarios map and the homogeneous territorial unit susceptibility map. The result of this study show that the susceptibility of slope to the landslides is mainly influenced by geological setting and geomorphological condition of the area. Another key aspect was the creation of a more detailed landslide inventory map, considering typology and state of activity. These allow to identify with more detail all the areas affected by the stability phenomena. Furthermore, the introduction of the HTU S5 class is a further step forward in the knowledge of the stability condition, because areas originally identified as stable may be involved in the landslide movement, which needs to be considered when applying the result of the susceptibility mapping. To sum up, this work shows the first application of the homogeneous territorial units method in the southern sector of the Tamaro River Basin, at more detailed scale than the hydrogeological setting plane map. It is worth to point out that homogeneous territorial unit approach is able to rank landslide susceptibility on slopes where no evidence of previous landslide activity can be recognized. Finally, the accuracy and the simplicity of the method encourage a further application, not only for areas where structurally complex formations are present, but also for those areas with denser landslide occurrence. Thanks for the attention.
Thank you, Professor Ranaldo. Thank you for your remarkable presentation. I thank the speaker and the authors of this presentation for the interesting work that will be deepened in the next discussion managed by Professor Domenico Calcaterra. Please, Mimmo, I remind you that the time available is 35 minutes and it will end at the 12:40. Please, Mimmo.
Okay, thank you, Giorgio. Good morning, everybody. As reminded by Giorgio, I'm Domenico Calcaterra, Mimmo for some of you. I'm an engineering geologist from the Federico II University of Naples. And a few suggestions just to manage at our best this discussion. At the bottom of your screen, you will find an icon, D&R, which is the Italian acronym for question and answer. So you are invited to write down your question in the boxes, in that box, possibly writing also your country or institution. And then I'll read the question. Of course, you should have highlight the presenter to whom is the question is addressed. We have already a question, or at least a proposal of speech by our boss, Luciano Picarelli, who is invited to make his question. Please, Luciano. Luciano has some question for Kei Ogata, one of our lecturer, and the point is, I'm reading. Luciano appreciated your focus on the heterogeneity and anisotropy of complex formation indicated as melange. As a geotechnical engineer, I would outline that discontinuities play an equally important role that has not been outlined in the same way. I believe that more emphasis should be given to this point due to its influence on both pore water pressure regime and available shear strength. Okay, you are invited to make some comment on this statement by Luciano, please.
Yes, I'm here. I was actually switching to my headphones, so I didn't get the full question. Can you repeat it a little bit?
You can read the DNR box.
Oh, no, I can't. I don't see any question in my Q&A.
I'll repeat. The main point raised by Luciano is as a geotechnical engineer, I would outline that discontinuities play an equally important role that has not been outlined in the same way, equally with respect with heterogeneity and anisotropy. Luciano believes that more emphasis should be given to this point due its influence on both pore water pressure regime and available shear strength. Please, Kate.
Yeah, I actually completely agree. I didn't focus too much into the mechanical discontinuities. They are actually intrinsic in the types of melange I've been showing. But it is definitely a point. I was actually focusing more on the overall say mechanical behavior. So, but there is quite a difference in with respect to this, especially for sedimentary melange, where are actually preserved. The internal discontinuities are actually welded in most cases, while the boundary contacts are pretty sharp. On the other hand, for tectonic melange, both the internal discontinuities and the external ones are pretty sharp and with not with actually strong mechanical decoupling. For diapteric ones, you have actually both situations from the marginal parts into the core. And that definitely has a huge implication, because those welded or unwelded discontinuities may drive fluids, as Professor Piccarelli actually outlined. So within the evolution, within the orogenic belt, this may drive differential poropermeability and pathways, and therefore also different mineralization, and therefore different competency for different parts of those melanges. Well, this is the long story short, but I don't know if I kind of answered the question or touch it a little bit.
Okay, thank you, Kay. Luciano, any reply?
Okay, thank you. Now, it was for me important to outline that these complex formations are characterized from one side by a strong heterogeneity, as shown and outlined by Professor Ogata, but at the same time, the overall behavior of this formation on site is strongly controlled by the discontinuities, which presents different characteristics in terms of persistency, in terms of friction, and so on. My objective was to outline that they have the same importance as the heterogeneity in the structurally complex formations. Hope to have been clear.
Yeah, and in turn they influence the overall behavior as well. So I completely agree.
Okay, thank you. Thank you.
Thank you both. I have a question for you, Luciano and Gianfranco, on your paper. Considering your huge experiences on structurally complex formation in southern Italy, which are the peculiarities, the differences or analogies shown by Flysch Rosso formation in comparison with other formations you have already studied, such as especially varicolored clays, which according to many authors are, if not the same, but very similar to Flysch Rosso?
It is a quite complicated question for us, because we have not the same experience as you, Professor Calcaterra, regarding these formations. For us, varicolored clays and Flysch rock and red Flysch are similar formations because their main characteristics are a strong heterogeneity and the widespread presence of a shear discontinuity. And this naturally affects the stiffness, shear strength, and also the pore water regime, which is controlled by the open discontinuities. I cannot see any significant difference, because even in the same formation, for instance, in the red Flysch, or for instance, in varicolored clays, we can have stronger differences from point to point. So it is not so easy to have a complete framework about these formations. So my answer naturally is not satisfying for you, but I think that there are not models that can frame in a rational way these formations.
If I can integrate the answer, I think that as regard the pellitic component, I agree with Professor Piccarelli. They are very similar as regard the mechanical and the hydraulic behavior, but also as regard the structural layout. But I think that as regard the lithological aspect, I think that the variability of the red fleece is major. I don't know other formation that has the same variability of the red fleece, and also in a very small, at a very small distance, like 100 meters and so on. This is my last experience that I had from this last investigation that we, with Professor Santo, we made in Campania, in the northern, in the east of the Campania.
Thank you, Gianfranco, and also Luciano. Conversely, from Luciano's opinion, I'm satisfied with your replies. So thank you again. There is a question from Muhammad Arshad, but it's not clear who is the presenter who has to reply. The question is, which type of methods can be used to characterize the slope, and how warning system work to predict the landslide? Muhammad, if you can write down the name of the presenter so he can reply to you, please. In the meantime, I have a question for Professor Strom, who I thank very much for his scenic presentation, as in many other cases. The question is, Professor Strom, in the paper you wrote down about prehistoric rock avalanches, and you mentioned in your conclusion that evidently this huge phenomena should be related to past climatic ages or moments of the Quaternary. Do you think that at least partially these mass movements can be remobilized, reactivated, for example, by earthquakes, or we have to consider them definitely as paleo landslides or relic landslides? Thank you.
Thank you for your question. You see, generally, what we could see, most of these deposits, they had already collapsed up to the lowest part of the relief. And of course, a strong earthquake can somehow affect them, but it is quite unlikely that they will cause significant reactivation of them as rock avalanches or whatever, or large landslides. There might be fractures, there might be some local slides, but they are now resting at the base of the slope. Of course, earthquakes as potential triggers of this phenomena cannot be excluded, but it seems that geological structure at such sites forms good preconditions for slope failures, for which maybe earthquakes are not necessary, or it will be very difficult to prove that they played a special role. It cannot be excluded, of course, but I do not see the way now how to, at the present level of knowledge of properties of whatever, how it can be proved.
Thank you again, Professor Strom. Waiting for some other question from the audience, I will ask a couple of questions to Igor Peszewski. First curiosity, Igor, you fixed some thresholds as regards the tensor analysis. A couple of them seem quite low if compared to the literature choices, especially the number of coherent pixels. If I remember well, you fixed this number at 1, and also the velocity of the PS considered as relevant, as coherent, which is 2 millimeters. Could you explain why you made such choice, please?
Yes, I will try to explain this. I see Dario is here. Maybe he can also add something to it. The first problem with the INSAR was that the coverage from the Sentinel was not so good, and we tried to, let's say, exploit maximum data which was available in order to detect some movements. And this is why we decided to go at such a low, let's say, susceptibility, or how to say, on 2 millimeters. So this is the only reason, and it only should serve like indications of what we should expect, because we don't have anything on the ground to compare with. So there is no more ground monitoring of any kind. So this is only like to get indications, and after that to continue with future works and to try to install, let's say, monitoring of on the most suspicious landslides, indicative landslides, and so on. So this is the main reason why we go with these parameters.
Yes, if
Dario,
I just can add
can
some,
also...
I totally agree with Professor Calcaterra that this is a strange way of operating with this kind of data. The problem, as Igor said, that the situation here was not that easy, because about the area, the basic data were totally or almost lacking. So that our colleagues were keen to have information about everything that was giving information about moving. So that was just a preliminary step. And of course, the hot spots, let's say, that in some way were identified, were areas for which they had no information about landsliding. And the idea was that it was just a way to detect some area where more detailed studies should be addressed. The problem is that we were not starting from an available inventory in that case. So let's say we were not so conservative as usual when using this kind of data. About the threshold, it was 2 millimeters per year, if I remember well. So that it is almost typical in that area. But the problem is that, of course, we cannot validate up to now on the ground with the ground-based data. Of course, these are further steps, because this was just the first step of this project. So.
Thank you, Dario, and also Igor. I have another curiosity regarding your paper. In your conclusion, you underline that the analysis, the susceptibility analysis on the debris flow was a sort of exercise, considering that you have only one event out of more or less 140. Also, the geological setting clearly evidences that probably debris flows are not typical, at least considering the bedrock geology, because you don't mention weathering materials, weather products. But you have a quite good number of translational slides, at least in percentage with respect to the total. Why didn't you try to carry out this kind of analysis on the group of landslides more represented within the number you have inventory?
Yes. So the problem here is that when we compare the size of the area and the number of landslides, it is very, let's say, very small. And most of the landslides are belonging to the lower elevations. So what we obtain with the FLOWAR model for the higher elevations is actually not, let's say, observed in the field. And this is why we need to be careful, let's say, when continuing on the watershed level, when we analyze the debris flow susceptibility to carefully take a look on the higher elevations, because we have a very steep slopes, very angular rocks here, and the case that they will develop into debris flow, it's not so, let's say, possible. Is to be expected on lower elevations below, let's say, below the, how you say, below the forest belt. And above the forest belt, we don't believe that there is a chance to have a, let's say, large amount of debris flows that can finish into the main streams. So this is the main reason.
Okay, thank you. It's evident, as already highlighted by Professor Peduto, that you are at the beginning of a study, and there is a huge job to carry on in the future, evidently. Just to say, within the fixed time, I have a couple of short questions also for the last paper. Mirko, it's for you. First one, have you made any comparison with the official maps existing in Italy on the landslide inventory and hazard?
No, because for the study area, an official landslide susceptibility map doesn't exist. To the moment, it is possible to do only the comparison with the official landslide risk map.
You mean that it's not possible to, it's not available an hazard map?
The only no.
Okay.
No, it's not available.
Okay. Another question is related to the method you used in this preliminary work, which is essentially based on field work and earthquake interpretation. So what the previous colleagues define as conventional methods. Do you think that the work could be improved by applying some innovative technology, for example, DINSA technology? Please.
Considering the maximum expected velocity of a landslide, it's possible to use satellite techniques, for example, SAR interferometry, to investigate with more detail the state of activity of the landslides.
Okay, thank you, Mirko. I don't know if there are any further questions from the either the organizer, the speakers themselves among them, or from the, because in the question and answer box.
I saw a question from Matteo.
Matteo Berti, yes. Yes, thank you, Luca. A question for Professor Ruccioli. Please, Matteo.
Okay, thank you, Mimo.
Ciao.
Yes, I have a question for Professor Ruccioli. It's let's say a vintage question, old-fashioned question, because I was wondering if there are any news regarding the difficult geotechnical characterization, mainly laboratory tests, I mean, of these stiff clays. You know much better than me that there are a lot of problems with lithorelicts, small fragments of stiff clays and so on. And all this kind of stuff makes so difficult also the, just the plasticity test, for example. So now, and I remember there were a number of papers late in the 70s on these subjects. So I was wondering if there's something news about this, or if the research is still progressing. What's your opinion on this?
Yes, it's a great problem because it's very difficult to make a test experimentation on these soils. One of the problems is the presence of the lithorelicts, but also the presence of discontinuity. And for that, many specimens are not useful. Other one are useful, yes, but we ask if they are representative of the pelitic components. And for that, these remain a great problem. But the major problem is how is representative the pelitic behavior respect to the on-site behavior. And this is an open challenge, in my opinion. For that, it's very important to organize a symposium as this and to have in the future a strong activity of this fact. But I think that Professor Picarelli, that is here, has a large experience on the experimentation of the soils. If you can add some considerations.
I can confirm what you are saying. Yes, the problem is very complicated. My point is that based on my experiences, I see that the laboratories are closing and people are more and more engaged in numerical analysis, using models that are not useful to describe the behavior of these materials. So my point is we should open our laboratory and we should try to examine the behavior of these materials. In any case, we have a good experience on that. As you know, we have written, especially in the 90s and at the end of last century, a number of papers. And we have been able to recognize, at least in the case of what we call scaly clay shales, the major role of discontinuities. So the major role of fabric with respect to other parameters such as porosity or liquidity limit or grain size on the behavior of these materials. The role of fabric is very important. So, but to analyze that, we should use large samples, criteria for good retrieving of undisturbed specimens, samples, and good laboratory tools. So it is quite complicated. In any case, we have been able to recognize the role of the minor shears, for instance, on the behavior of scaly clay shales, which in some way play the same role as porosity in sense, because they control sort of dilatancy of the materials, which coupled with the friction angle along the shear discontinuities, which is very close to the residual value, influence the shear strength of the material. But I know that my response is so only partial. We should open our laboratories rather than close them.
I fully agree with you. Thank you. Thank you. Thank you very much.
Well, I think the session is closing. We have used all the time available assigned to us. And I thank you all, the speaker, Kay as a lecturer, and all the attendees for having participated to this session. And now it's time to pass to the next event, which is the lecture given by Professor Pignon. See you. Bye-bye.